turns out there's an interesting connection between these so-called hyperbolic functions and trig functions. Hyperbolic functions, what they are, they're combinations of e to the x and e to the minus x. Hyperbolic functions follow some combination, and I'll explain what each one is here in just a second, but the reason they're so-called hyperbolic because they are, you have your trig functions, which are, like your cosine and your sine are from your unit circle, right? X, y. X is the cosine of theta. You with me there? Remember that? Okay. Well, the hyperbolic functions, they have the same relationship, but with the hyperbola. The unit hyperbola is x squared plus y minus y squared equals 1. This is x squared plus y squared equals 1. The xy here plays the same sort of role, the x and the y. So that's why they're called hyperbolic functions. They're from the hyperbola. But anyway, all that said, there's a connection there, and so you kind of use trig-looking names, except with the h for hyperbola, right? So I've got the sine with an h. That function is this combination of e to the x, e to the x minus e to the minus x over 2. It turns out is called, this is a hyperbolic sign. And its symbol is sine with an h, okay? And, interesting here enough, it's pronounced cinch. Instead of sine, we call it cinch. Or cinch, I guess, but cinch sounds better to me. All right, cinch. And so, if you, what you do is you do the cinch of, just numbers, like you do sine of just numbers or angles. But here, the cinch of 3, well, the value of it is it just comes from this combination of e to the x. So it's e to the 3 minus e to the minus 3 over 2. That's what cinch of 3 would be. Just plugging in the x to be 3. All right. Let me go ahead and give you then. Now, of course, that as far as simplifying, you're not going to be able to simplify that very much. You can round it off. I think if you do the rounding, you get that's about 10.0179. And the most graphing calculators do have cinch on them. So if you ever see that, that's what it means. Okay. Well, we've got cinch. So guess what else we've got? The hyperbolic cosine. We've got it. Cosh. It's e to the x plus e to the minus x over 2. E to the x plus e to the minus x over 2. Now, here's where we can really see kind of the connections coming into play. All right, so we've got, that's cosh. Then we have tanh, the hyperbolic tangent. Well, the good news about it is it follows suit with the identity. Tangent is sine over cosine. Tanh is cinch over cosh. And so if you work that out, it turns out it's e to the x minus e to the minus x over e to the x plus e to the minus x. But I would just remember that, right? Sinh over cosh. So guess what? The hyperbolic secant, sech, well, it's 1 over the cosh. Just like secant is 1 over cosine, sech, hyperbolic secant is 1 over cosh, and cosech, hyperbolic cosecant, is 1 over sinh. Oh, and there's one more. What did I leave off? Cotangent. It's 1 over the tangent. So anyway, that's good news about it. Okay? Now, one other note here. Again, a lot of calculators do have these hyperbolics, but a lot of them just have, just like on the regular trig functions or the trig functions, you only have sine, cosine, and tangent. So let's talk about it. What if they wanted us to do sech of 1? Well, sech of 1, just to make it clear here, sech of 1, and sech is the reciprocal of the cosh. And so cosh is this, so sech, I didn't write it out over there, but that would be the reciprocal of that, right? So it would be 2 over, so this would be cosh of 1. So it would be 2 over, plug in x to be 1, so it would be 2 over e to the 1 plus e to the minus 1. If you wanted to know the value, get a value for sech. It turns out it's about 0.648 if you plug all that in. Okay? All right, well, of course, that's what they are. We're in calculus, so we've got to do the calculus of these, right? We've got to do derivatives and antiderivatives. Well, they're not too terribly difficult. Here's the way it works. Since I've got cosh up here, let's just talk about what the derivative of it would be. Well, if you start out here, kind of verifying this, what it is, what might you guess? Well, if cosine, the derivative of it is minus the sine, so we might guess minus sinh. Let's see. Since cosh is this, right, it's e to the x plus e to the minus x over 2, I want to do the derivative with respect to x of that. Well, that's why we bring it up here, because I've done the derivative of these, right? Of course, the derivative of this 2, I can just say that's a half times e to the x plus e to the minus x. Let's just, so I don't have to pull out the quotient rule and all that. But yeah, it's just basically doing these two. The derivative of e to the x. So it's 1/2. What's the derivative of e to the x? E to the x. What's the derivative of e to the minus x? Well, the derivative of e to the minus x would be e to the minus x, but then, since I've got minus x just x, don't I have to multiply that by the derivative of minus x? Derivative of minus x is minus 1. So I wind up with 1/2 times e to the x, and that's just minus e to the minus x. Or, to put it another way, it's 1/2 e to the x. No, I want to put it another way. It's e to the x plus, minus e to the minus x over 2. Well, that might look familiar. I've erased it, but remember what sinh was? sinh was e to the x minus e to the minus x over 2. Isn't that exactly what I've got there? Turns out the derivative of cosh is not minus sinh, it's just sinh. So that's a little bit different than the trig function cosine, but nonetheless, that's what it is. It turns out the derivative of cosh is just positive sinh. Well, long story short here, let me just give you the rundown here. The derivative of cosh is sinh. The derivative of sinh turns out is just cosh. That's pretty nice. They're vice versa, okay? One's the derivative of the other. That's kind of what we wish the trig functions were, but oh well, negative sign. The d dx, the derivative of the tangent, well, the derivative of tangent is secant squared. Turns out the derivative of tangent is sec squared. So that's nice. And then just for fun here, the d dx of, let's do sec. Turns out it's minus cosec, minus sec tangent. So that's a lot like secant. Secant is secant tangent. The only thing it's a minus secant tangent. The d dx of cosec is minus cosec. Oops, I forgot the x. Cotangent. And the d dx of cotangent is minus cosec squared. So they're all similar to their trig function counterparts, except the negatives are different places. This in trig function, secant is not a negative. It's a positive secant tangent, but this is a negative secant tangent. This, like I said, we already mentioned this one. It's minus sign in trig function. I guess that's the two differences, this one and this one. So anyway, interesting little thing. Okay? All right, so here's one to try out. So we've got the cosh, y equals the cosh of the square root of 1 plus x squared. First thing I might want to do there is change that over to a power, square root. Change that to a power, 1/2 power. And then I have, don't I have there chain rule, inside and outside? Okay, so the derivative then, the derivative of the outside, well, there's my cosh. The derivative of cosh, sinh. So it would be the sinh, the inside stays the same, so this would be sinh of 1 plus x squared to the 1/2. Now, the derivative of the inside, well, actually there, let's think about that. The inside actually has an inside and outside part too, doesn't it? So I have to do kind of multiple chain rule here. I have to do the 1/2 power, so bring down the 1/2, and then subtract 1 from the power, so I get a minus 1/2. But I still need to do the inside of the inside. So what else do I need here? The inside derivative, 2x. With me there? Well, these twos cancel out. I could do it because that's a minus. Let's write it this way. And you can write it, leave it that way, or let's write it this way. Sinh, that would be the square root of 1 plus x squared. This would get flipped over, so I'd have the square root then, 1 plus x squared on the bottom. That's probably how you would see that all written out. Okay? Question? Concern? Anything? Okay? All right. Here's another. What about the tanh squared x? Well, if you remember, one like this, probably the way we want to think of it is go ahead and write that, rewrite that. Doesn't that mean tanh of x squared? Because then we can see there our inside and outside. Actually, the tanh is on the inside, part of the outside. So in my chain rule, to do the derivative, I do the outside, which is the power. So bring down the power, leave the inside the same, subtract 1 from the power, so it'd just be tanh to the first. Then I'd multiply by the derivative of the inside, and the derivative of that tanh, remember its counterpart is, it's similar to that. Tangent is secant squared, so tanh is sech squared. So it's just 2 tanh sech squared. One more. Then we'll do antiderivatives, okay? G of x cosh 2x times sinh x squared. Well, what do we got there? Besides the hyperbolic, I've got product rule, don't I? First on second. Use the old product rule there. So it would be the first, the cosh, times the derivative of the second. Well, the derivative of sinh is cosh. But it's sinh x squared, so I do have to multiply by derivative of the inside too, so it'd be 2x multiplied by that. Then I do that, reverse it, do the second one, sinh of x squared, times the derivative of the first. Well, the derivative of cosh is sinh, so I'd have sinh of 2x. Then times the derivative of the inside be 2, so it'd be that right there. And like trig functions, they usually write these that aren't don't have the hyperbolics on them. Write those up front here, so we have 2x times the cosh of 2x times the cosh of x squared plus 2 times the sinh of x squared, sinh of 2x. Not totally necessary, but that's generally speaking what they would do. Just move those pieces up front. Okay? Nothing to it, right? Well, the good thing about those hyperbolics, too, is that since the derivative of cosh is sinh and the derivative of sinh is cosh, the antiderivatives, well, they're pretty straightforward, too. If you have the integral of cosh, what is that going to be? Be sinh, wouldn't it? Plus c. The integral of sinh, the antiderivative, in other words, is going to be cosh. You don't have to worry about the signs on those. And then the antiderivative of sech squared, I think, is the main three that we'll focus in on here. That would be the tanh. And so the main one to emphasize here, now what if I have the integral of cosh of 5x dx? Well, that's not quite sinh. Almost is. All I have to do there, because of the cosh of 5x, well, it's a little simple u substitution, isn't it? Let u be that 5x. And so du would be 5 dx. So du over 5 would be dx. So that's all it's going to change here is that, yeah, it's going to be cosh of u and then du over 5. So, yeah, then it's just sinh. All right, so it'd be the 1/5 would be our factor up front there. The cosh is the sinh. So I'd have 1/5 the sinh of u and then go back to the x. So it'd be 1/5 the sinh of 5x. See? Okay? So the good thing about it, I mean, it's totally different. Totally different than the trig functions. I mean, this cosh, the sinh is, you know, it's combinations of e to the x. Totally different thing, but the good thing is it's, you know, counterpart, okay, more or less, little slight variations, works the same as the trig function.